My name is and I want to talk about network reconfigurations today. Operators reconfigure their networks very often, and they would like to do so without affecting customer traffic. Let's look at an example. Here we have a small network with two external peers. Both peers advertise prefixes via BGP, but the network prefers routes towards the left due to a higher local preference. Let's say we now want to remove the BGP session on the left due to a change in business relationships or just for regular maintenance. This makes the network then forward to the right. But simply removing that session is not a good idea, because as soon as we do so, packets would get dropped at the left border router. But because that one doesn't yet know about the alternative route. And it doesn't know so until the network has fully converged. So how bad are those temporary black holes? And we performed some measurements, and we saw that those black holes can persist for 2 seconds, even in a very small network with only around 1,000 prefixes. So there is certainly a better way, and which is in this case, to first move all the traffic to the right before removing the session. And we can do so by, for instance, lowering the local preference, which is actually what best practice suggests in this case. While this is certainly better, there is still a chance that anomalies can occur. And this is because BGP converges as a distributed process, and it is very hard to predict. Certain messages can get delayed, or just some routers are faster than others. Now, a way to perform those reconfigurations safely in any transient state is to decouple how the control plane converges from how the data plane updates. An existing system that does so is called ships in the night. And what it does is it runs the initial and the final configuration simultaneously in the network. And only the initial configuration actually has an effect on the packet forwarding, while the final one is sort of there like a shadow. It then lets the final configuration converge. And then it gradually migrates the network by selecting a router and making it so that it forwards according to the final configuration instead of the initial one. Now this decoupling from converging the control plane and the data plane allows it to reconfigure any network safely, but at a high cost, because it requires a lot of resources, both in memory and in compute, because essentially it duplicates the control plane. And also it needs special software. But we can achieve that decoupling only using static routes. And to do so, we just fix the initial forwarding state using static routes everywhere. And then we reconfigure BGP and let it converge. But this does not affect the forwarding because we have the static routes there. And as soon as the network has converged, we can slowly start removing those static routes from the right to the left. And this technique allows us to reconfigure any network safely, but during reconfiguration, the network is vulnerable to unforeseen events such as failures due to the nature of static routes, and the static routes cannot react to those events. So to summarize, we want to reconfigure BGP. We want to do it safely, meaning it should be safe both in the steady and in any transient state. But we want to do it efficiently without requiring lots of resources, and we want to do it in BGP itself to maintain the reactivity inherent to those distributed routing protocols. And we want to do that in networks today, so we don't want to require any special software or additional device in the network. So our approach for solving that problem is not to decouple the BGP from the data plane during convergence, but instead to make them converge together in a controlled way. In other words, we precisely control each router and when it updates from the initial to the final route. And when it does so, it also updates its forwarding state accordingly. To make a single router update in a controlled way, we need 3 properties. First, the router must still select the initial route. And second, it must receive the final route without yet selecting it. And finally, once we update the router, it cannot cause any other router to change. So let's see how those rules apply to the example that we have seen before. Now, I no longer show the forwarding state, but now I show how BGP routes propagate. So here, the blue route, which is the initial route, is the border router on the left propagates that one to every other router in the network, while the orange route, which is the final one, is only advertised by the external network on the right. So now the border router on the right selects the initial route and knows about the final route, so we can make that one update. And if we do so in a smart way, we can make sure that all other routers receive the final route while still preferring the initial one. And in the paper, we show how we can do that in general. So now every router knows selects the initial route and knows the final route, so we can make them change just like before. And we can do so in any order. So essentially, we now move the problem to how the routes propagate. But reasoning about how the routes propagate is very difficult in general for BGP due to its many features. Concretely, features that allow BGP to scale to large networks, like route reflection. Those features reduce route visibility in the network. Let's consider an example here where we have a single route reflector in a network. The border router on the left will now advertise its route to the route reflector, and that one will then reflect its routes to all the others in the network. So we can still start with the border router on the right, making it to update it, but now we're stuck because the route reflector now, it selects the old route, it knows about the new route, but when we make a change, then others will follow. And now we can no longer control which router would update before another one. To solve this issue, we temporarily adapt the propagation graph of BGP by adding temporary BGP sessions. Now, the big challenge is how we can achieve that in general, because it should work for any arbitrary configuration and reconfiguration scenario, like removing or adding BGP sessions, both external and internal, or changing external or internal route maps, or doing multiple of those things together. But it should also satisfy an arbitrary specification, and it should satisfy it in every intermediate state. The specification can be as simple as reachability, but it can also combine policies like traffic isolation or waypointing. So we present Chameleon, a system that can actually perform those reconfigurations safely. What Chameleon does is it finds a schedule of routers to update. And this schedule must follow the propagation rules as I've described before, but it also must satisfy the specification at every time in that schedule. In addition, we want to perform the reconfiguration as quickly as possible, and we can do so by updating multiple routers in parallel, concurrently. And finally, we also want to add as little temporary BGP sessions as possible. So what Chameleon does is it formulates those constraints as an optimization problem and encodes them in an ILP, so that the ILP can then solve the problem efficiently. From that node schedule that the ILP solves, we then generate a set of reconfiguration commands. Those commands are regular BGP commands, but they introduce temporary configuration that is not present either in the initial or in the final configuration. Finally, Chameleon applies those commands one by one to the network in the ordering that it computes, and it enforces that ordering by checking for conditions and checking how far the network has already converged. And those conditions, Chameleon must only query one single entry in a routing table. So we perform measurements and validate Chameleon. And indeed, Chameleon can reconfigure a network without dropping any packets. Here in this graph, the blue, purple, and orange line represent the traffic that is leaving and different border routers, so you can see how the network changes. In the paper, we also present a large-scale evaluation of Chameleon. And as a summary, Chameleon is able to find a schedule of a large network with over 100 routers within less than 5 minutes. And also is able to safely apply the reconfiguration plan for this large reconfiguration in less than 5 minutes. Finally, Chameleon duplicates around 10% of the state, which is required to keep both the initial and the final route visible in the network at the same time. So, as a last remark, I want to redirect you to this link. Here you can visually and interactively see how Chameleon works directly in the browser. And you can see the reconfiguration plan it computes and play with it yourself.